Have you ever wondered about the invisible world of energy that's happening all around us all the time? You know, how something as simple as water evaporating off your skin can make you shiver. Or, and this is a weird one, how freezing something can actually release heat. Well, we're going to pull back the curtain on all of it and uncover the hidden energy transfers that shape our world. So, let's start with a couple of those everyday mysteries, things you've absolutely felt, but maybe you just didn't have the words to explain what was really going on.
First up, a feeling we've all had, right? You get out of a pool on a warm day, and suddenly you're cold. Why is that? Where is that chill actually coming from when the water evaporates?
And now for a real head-scratcher. Why is energy released when you make an ice cube? I mean, your brain tells you that freezing something should trap the cold or trap the energy, not let it go. It seems totally backward. To answer these, we need to get a couple of basic ideas down first.
And it all starts with a really simple but super powerful idea. Before we can track where the energy is going, we have to divide the world into just two parts, the system and the surroundings. First up is the system. And look, this is just a fancy science word for whatever it is we decide to focus on. It could be a chemical reaction or, that drop of water that's evaporating on your skin. That's our system.
So if that's the system, then the surroundings is, well, it's literally everything else. It's the air around the reaction, the glass beaker it's in, even your hand that's feeling the temperature change. It's the rest of the universe, basically.
So, check out this classic lab example. The chemicals mixing together inside the beaker, that's our system. Everything else, the glass, the air, the hand holding it, that's all part of the surroundings. Simple, right?
And here is the absolute key, the most important rule of the game. Energy never just disappears, it just moves. So any heat that's lost by the system has to be gained by the surroundings. And, of course, the opposite is true too. It's a perfect trade every single time.
Okay, so with this idea of energy just moving back and forth, we can finally talk about the two fundamental types of processes we're exploring today, the ones that pull heat in and the ones that push heat out. And this brings us to the two big words for today. On one side, we've got endothermic. Think endo, think in. Energy is going into the system. The system absorbs heat from its surroundings, and that's why it feels cold to us. On the other side is exothermic. Think exo, think exit. Energy is exiting the system, releasing heat to the surroundings, which, of course, feels hot.
Now, don't get bogged down by all the details on these graphs. Just look at the shape. It's like a hill. Endothermic processes are an uphill battle. They have to suck in energy from their surroundings just to get going. Exothermic processes, they're a satisfying downhill slide. They release all that pent-up energy and end up in a much more stable, lower energy state.
So let's make this real. What are some endothermic processes? Well, think about melting ice or boiling water. You have to add heat, right? You're putting energy in. Same with sublimation, when a solid turns straight into a gas. And guess what? Breaking chemical bonds also takes a ton of energy.
And yeah, you probably guessed it, the opposites are all exothermic. They're pushing that energy out. So freezing water into ice or watching steam condense on a cold window, those processes are actually releasing heat. And whenever new stable chemical bonds are formed, that's almost always a release of energy. All right, enough with the theory. Let's get to the fun stuff and see how this plays out in the real world, everywhere from your morning brew to a first aid cold pack.
This graph right here is the heating curve for water, and it's a perfect map of an endothermic journey. As you pump in energy, the temperature climbs. But then, wait, look at those flat spots. What's happening there? It's so cool. That's where all the energy is going into breaking the bonds, turning solid ice into liquid water or liquid water into steam. The temperature actually stops rising until the change is complete.
And if we run it backwards, we get the cooling curve, the exothermic story. As steam condenses back to water and water freezes into ice, it goes downhill, releasing all that stored energy. This, by the way, is why a steam burn is so dangerous. It's not just that the water's hot, it's that when the steam hits your skin, it releases this huge extra burst of energy as it turns back into a liquid. That's what does the real damage.
What about instant coffee? Ever wonder how they make that stuff? Well, it's a two-step dance of energy. First, they freeze the liquid coffee, which we now know is an exothermic process. But then comes the magic, sublimation. They put the frozen coffee in a vacuum, and the ice turns directly into a gas, skipping the liquid phase entirely. And to make that massive jump, the ice has to absorb a ton of energy. That's a powerful endothermic process.
Okay, time for a little puzzle. This is exactly what happens inside one of those instant cold packs you shake to activate. You take some ammonium nitrate and dissolve it in water. And when you do, the temperature drops a lot. It goes from about 22 degrees Celsius all the way down to 17. It gets noticeably colder.
So based on that one single observation, the fact that the water got colder, what do you think? Did heat enter the system, the dissolving salt, or did heat leave it?
And the answer is it's endothermic. Heat actually entered the system. The dissolving salt is the system, and to break apart, it has to absorb energy. It's literally stealing heat from its surroundings, the water, and that's why the whole solution feels so cold to the touch. Pretty neat, huh? So let's bring it all home. Let's see how this new lens can kind of change how you see the world around you every day.
If there is one thing you remember from all of this, let it be this. A change in temperature is your clue. Whenever you feel something get hotter or colder, you're not just feeling a temperature. You are feeling the physical result of an invisible transfer of energy. You are literally witnessing energy on the move.
And that brings us full circle, right back to our very first mystery. That chill you feel when you get out of the water, it's a classic endothermic process. The water on your skin is the system. To evaporate and turn into a gas, it has to absorb energy. And where does it get that energy? It pulls it directly from your body. That's why you feel cold.
So, I'm going to leave you with the challenge. Now that you know the science, a change in temperature, a change from solid to liquid to gas, what hidden energy transfers can you spot around you today? A candle burning, a puddle drying in the sun, an ice pack getting cold? It's this constant, invisible dance of energy. And now, you know the steps. All you have to do is start watching.